Hey guys, I have only a very short presentation today, so I'm not going to say anything new. I just want to go through some logistics for the exam and just briefly go through it. I already put on Canvas and show it some practice materials and also a list of topics which I have to report. So I'm basically going to do here is reiterate these topics. That's it. So first remark about the exam. 25 points, just like the assignments. You estimate to make it alone, of course, obviously. Since it's the only real grading that is really truly individual, it is a must pass. So you have to have the rules of the work that is then 5.5 out of 10 points. It's open material, so or open book, whatever you like to call it. So you can bring any material you like. I'm fine with keeping it digital, but then you will have to use your device on airplane mode, which means that you will probably have to download it before it. So but other than that, that's fine. Right, so these are the topics we discussed, more or less. So the bulk of the material is just, of course, in slides. Some of it in chapters. The chapters are on Canvas. The main book chapters are those from Geheimer 1, 2, and 3 that give you a longer overview of biomedical optics, and which also have some tidbits here and there about topics we discussed. Chapter 5 was about Carlos collections. And chapter 18 is a chapter on well, the important things, of course, the fundamental optical properties, how we describe scattering absorption, efficiencies, coefficients, cross sections, what are their relations, how do you relate, for instance, to power, short power, calculate the efficiency from the unitless, if you multiply with the geometrical cross section, you get something that is an area, so like units of square meter, and if you multiply with number densities, you get of course, you can. So we have this for absorption. We also have this for scattering. Same set of functions. And essentially, you can do this for any type of process. Where you define efficiency, you can do this scaling through two coefficients to a cross section to a coefficient. For example, the efficiency for fluorescence is by now a few percent maybe. Which means you could also calculate the cross section for fluorescence, coefficient for fluorescence, same thing for Raman spectrum. All right. That's the coefficients. So the main law that governs that, of course, is the Pierce law. That's a must know. And then we discussed this peculiar effect that happens if you start organizing absorption models. If you are free floating, or let's say totally randomly floating in the suspension and do a measurement experiment, measure a given absorption coefficient. If you would then encapsulate the same amount of molecules inside particles, so regions in your sample where there is multiple absorption and regions where there is not, and we do the same experiment, measure a different absorption coefficient, simply because these particles are not, these molecules are not organized. These were the formulas that came along with that. 3 absorption coefficients are there. So the absorption coefficient of the suspension is when the molecules are inside the particles. The second experiment that we described, if they were in the solution, the first experiment we described. Green is the UA of the molecular UA, if you like. And this would be what you would measure if you would take one particle, treat that as the QA. You would do a transmission measurement on only one particle, that is the absorption coefficient. Now, specifically for blood, then of course the suspension would be red blood cells, which contain the hemoglobin molecules. If you lyse red blood cells, you get a hemoglobin solution. Measurement of one single red blood cell, you measure the UA of hemoglobin, given the green data. As for absorption spectra, be familiar with how the absorption spectra of the most important compounds look like more or less, so beyond water. So know that water absorbs not so much invisible. It's easy, of course, that hemoglobin has distinct absorption peaks and that this can also influence, for example, the choice of wavelengths if you want to do a particular type of measurement. So, for example, if you look at the OCT of the retina, what kind of wavelengths would you choose?
Longer wavelengths, right? Because of the water, because there's this dip around 800 to a longer wavelength, so the absorption coefficient is lower, so you can penetrate deeper.
Okay.
That's it.
So the reasoning is correct, but the conclusion not there. So that's why you would use short wavelengths.
Because then it's not a
I'm sorry.
Yeah, I know what you're saying. Yeah, so you
frequency wavelength inversion. Yeah.
So they would pick something around typically 800 nanometers. The double pass through the eyes. It's easy. If you would do the same measurement within the skin, where the water content is much less, you can go to a longer wavelength. Why would you do that? Why not stick with it?
There isn't a lot of water in the skin.
No. It's still the absorption is lower at 800. So why would you
Penetrates deeper.
Yeah, the second effect, of course, there is also scattering involved. And the scattering generally decreases with wavelengths. If you go to longer wavelengths, you have less scattering strength, so that means that light penetrates further, you can make images. And it's always displayed. So an absorption and scattering that will, for a given application, will determine what kind of wavelengths you need. So that kind of reasoning is something that we try to apply all the time, and then basically the most important spectra to take into account are those because they dominate. Right, well, this is the same story about the coefficients and the cross sections of scattering. For scattering, it's convenient to make it a little bit more complicated and find the scattering coefficient as the density of scattering cross section. So if all the particles are the same, you just multiply the scattering cross section with n, divide by the volume, then get the product of density times the scattering cross section. If you have different particles, you just add the individual scattering cross sections and get defined by, and then divide by volume. Yeah, so forget this for individual particles. That also means that if we take we can interpret the scattering coefficient as a probability of scattering prevalent length. Absorption coefficient is the probability of absorption prevalent length. Every coefficient is the probability of let's say interaction prevalent length. So that means that the reciprocal of US in this case, the scattering coefficient is simply the mean free path between space and time. That is something that translates to the other coefficients as well. All right. So we discussed different scattering theories. So I'd like to know what the inputs for the scattering theories are. Discussed it many times. Particle size, wavelength, refractive index of the particle itself and its surrounding. And then we had a couple of scattering theories that described that were convenient for different sizes of particles compared to wavelengths. So for the shorter wavelengths, for a shorter smaller ratio, I should say, from particle radius to wavelength, the radius theory. It also describes the scattering by dipole. If you go to very large particles, then you're in the realm of geometrical scattering. Scattering efficiency is 2. Scattering cross section is 2 times the geometrical cross section. And anything in between, if it's a spherical particle, you can describe it B theory. Of course, B theory is not something you can write directly on a piece of paper. You need a computer, so that is why it's still beneficial to have these other theories for the inputs and ranges of fluid. Then we discussed a couple of lectures ago. We discussed a more general case where we described the material as a fluctuation of reflected index, or not really as a distribution of reflected index. So M is the reflected index, and squared minus 1 is called scattering potential from this equation that compares these outer products, which describe polarization of light, any incident, and the total field over here. This would be the result derived straight from Maxwell's equations that would describe the scatter field. Of course, the fact that you have the scatter field on the left-hand side and inside the integral is not so convenient. So one important approximation that we always do is the first order approximation, using that the incident field in the particle, the total field in the medium is the same as the incident field. Okay, this general formula could be worked out a little bit if we consider scattering by continuous random media. Then M became the spatial distribution of reflected index, and because we assume that it's random, we have to take averages, ensemble averages over all the. It's basically the assignment of the model. For the scattering process, also described, of course, by the phase function, it describes the angular redistribution of the light. Average cosine of the scattering inputs, so larger particles have higher scattering anisotropies, which means that they scatter light predominantly in the forward direction, and smaller particles have an isotropic scattering pattern, so it's used d value is closer to 0. Then we had this wonderful effect of scattering by multiple particles at the same time, where when the positions of the particles is not completely random, it's sometimes not strange or does, because their size is fixed. Otherwise, you cannot operate in space. If you ignore this effects, then you can just add scattering intensities. If you take them properly into account, you first have to add scattering fields and then square that to get scattering. The way that works out mathematically is that you can lump all these interference effects into the structure factor, function S. The easiest way to use that is by calculating, if you have identical particles, is to calculate the scattering cross-section and the phase function of that single particle using, let's say, mean theory or ray theory. And then the total scattering cross-section is n times, because we have n particles. And this integral term, the phase function multiplied with the structure factor, integrated over, and this accounts that for all the differences. That also means that scattering coefficient, the definition of the scattering coefficient is slightly adapted from what we had before. So it is still the density of total scattering cross-sections, but now in the total scattering cross-section, it appears these factors and also appears in the scattering coefficient. Then we write that a bit differently. So if you would not take into account interferences, you would get a scattering coefficient for, let's say, independent scattering, and then again the same factor is there to account for cooperative scattering and scattering effects. That structure factor was related to the pair correlation function. The correlation function describes how the medium is organized. The medium consists of particles, discrete particles. And if we calculated the effect, so this is scattering coefficient on the vertical axis versus volume fraction of particles in the medium. On the horizontal axis, if you ignore interference between the particles, the scattering coefficient simply scales linearly with volume fraction. But if you properly take it into account, you see that you can hardly see, but it still increases with volume fraction, but at a much shallow and more linear rate. It also means that the phase function for a single particle is here the blue line. The product of the phase function with the structure vector is then the red line here. So you'll also see that, that this means that the redistribution of the light is scattered. In general, it means that observed anisotropic effect and the observed G will decrease. Okay, then one of the workhorses of our field is Monte Carlo simulations, because in most situations, the boundary conditions or the geometries are too difficult to directly apply Maxwell's equations. So, other calculations, so that means that we have to use probabilistic methods. The recipe for Monte Carlo is simple. You bring an event, and it can be, for example, the trajectory of a photon going from A to B, bring sub-events. Calculate the probability of each events, multiply these if they're independent, then you can multiply them to obtain an event probability. If you have more than one way to get to the result of an event, so in this case that would be a different photon path, for example, then you can add all these probabilities, you can add these probabilities, and then get some probability for photons going from A to B. That then you take as a measure of what, or as a description of what you measure. Yeah, that's these are the things that came along with it. Again, the probabilistic meaning of the scattering and absorption coefficients, so the probability of units, the probability of scattering or absorption per unit length, and the reciprocal, that is the mean free path between such events. Materials of slides, good chapter, of course, and it was also a separate document. Then we briefly touched upon the transport and diffusion theory. We won't do so much with that this year, so just going to limit also what you would need to know about this to this list over here. Basically, what I would like you to remember from the system is that the most important radiometric quantity is the fluence rate. Fluence rate units volts per square meter. It describes the optical power that flows. So if you take a small area inside a medium, and the fluence rate describes all the optical power that flows through that area, regardless of direction. So it's the total time flow. That is important because if you want to do a laser treatment, for example, if you want to damage tissue, you need to calculate how much power you can deliver to a certain location. The fluence rate is then quantitative. You need to calculate the total amount of power. Then the transport equation was power balance of light flowing through a volume area. Yeah, to identify the different terms in there. We also very quickly established that it is only solvable for very simple and therefore not really realistic geometries. So yeah, that's basically where we left it, and then the way out of that is more or less the diffusion approximation. So what you do is you take the transport equation, you write all the quantities in there as a series expansion in spherical harmonics. All the inverse functions become series of Legendre polynomials, and you basically cut the series expansion short at 2 terms. And what you're left with then is what is very similar or equivalent to the description of diffusion of photons in the medium. Diffusion approximation, which means that you can use the diffusion laws, Fick's laws, to describe the photon transport. In that, a new bulk parameter appeared, the reduced scattering coefficient, which is prime, which is the product of US scattering coefficient and 1 minus the scattering coefficient. So it's times 1 minus G. Essentially, so if you take the reciprocal of that, then 1 over US would be the average step size between real scattering events, and 1 over US prime would be just some kind of equivalent step size that you would have if all the scattering was truly isotropic. So instead of a trajectory with many small steps with very small angles, so the photons will turn around eventually, you take larger steps and a much larger angles, and in the end that is equivalent. The diffusion coefficient that appears in fixed law and in the equations is D, is related to this scattering coefficient, reduced scattering coefficient 1/3 times this prime. And the limitations of this, because it is a series expansion, it truncated, is nearly limited. Basically, throw away the high frequencies, which means that near sources, near boundaries, near borders, become unreliable. So that is something that you need to take into account. Okay, we talked about causality, the Krams-Kronig relations. I showed you the derivation. It's nice if you can actually follow it. And again, it relates a little bit to the absorption spectra that we discussed earlier. So I'd like you to know that if there is an absorption, huge absorption peak in UV, that is actually the reason why the real positive effect decreases the wavelength, and that determines one of the reasons that the scattering coefficient decreases the wavelength. That way it is all connected. Let's see, then I have an OCT, of course. Spent quite a lot of time on that. We use interferometry, why we need broadband light sources. And we talked about signal formation. From a practical point of view, it works so well because the reference arm essentially acts as an amplifier of a very weak signal from the fissure. You have a very weak field with a huge field of the reference arm. You boost that into an intensity that is easy to measure. To calculate the actual electron resolutions, coherence lengths, given the characteristics of the light source, beamwidth translates into electron resolutions. Differences between time domain and spectral domain OCT, both in how they are built, what kind of equipment they use, and also that there's an advantage, speed advantage, or an SNR advantage for spectral domain OCT. So you can either measure much faster at the same signal to noise ratio, or you can keep measuring at the slow rate, you have a huge increase in signal to noise. So either way you can optimize it. And then what we talked about just a moment ago. So some common OCT wavelengths would be 800 nanometer for ophthalmology and 1300 nanometer for measurements in skin. Then what we just discussed, why would you choose a certain wavelength versus a different Raman, well, some physical properties. What is the difference between a Raman active and an ER active molecule? Drawing the Bonsky diagrams. Differences between Stokes Raman and anti-Stokes Raman, population of the electronic levels, these kind of things. You have to calculate Raman shifts. So if you're an excitation wavelength, then calculate the emission wavelength and vice versa, these kind of things. The efficiency of the Raman process is very low. Compare that with, for example, the efficiency of let's say, fluorescence of phosphorescence. Also, the time scale of which this process occurs. Raman is nearly instantaneous. Phosphorescence can take hours. All right, this is the same list as before. All right. Is there anything I can do for you?
There was some practice material.
Yes, put it on canvas. If more is needed, then let me know, and I'll put some. How much time does it stand us? I think it is the standard time, so I think that is 2 hours and 15 minutes. I think, from top. Some Tuesday, right?
Yes.
Yes.
How fast?
One was then by my pictures on Wednesday.
But we can bring our laptops, but
Yeah, you were later. Let me repeat that. So the rules are 25 months, so it's the same weight as the assignments. But because it's the only individual, the really truly individual moment, you have to pass it.
Yeah.
So you have to have 5.5 out of 10 points.
Okay.
So it's not 7 points. You have to get the pass. And other than that, it's open material. So you can bring anything you like, and because it tends to be quite a lot, I don't mind if you bring it on a laptop or an iPad. You have to put it on a couple of months.
Okay.
Which means that you have to download. But other than that, if you can just bring. Yeah, so it's just a few short questions with some individual calculations. So it's not a complete exam in the sense that you have to do. If you don't know question one, then you cannot make question two. It's just a few individual. Topics. That's all I can say. All right. Well, thank you very much. It was a pleasure.
It's on
Thanks.
Tuesday at warehouse.
Yeah.
Exactly.
And the science building. I'm just double checking.
It's where we have
WM69.
it's the same when we have lectures in it.
Oh.
No, that's the same room, but the same floor.
It says
Oh, same floor, yeah.
639 and 655.
Ah, yeah.
Oh.
Two
So it's
doors.
in a normal venture? I think if we're all together.
Yeah.
They're far too far.
Yeah, they always schedule two rooms because of. No, if you can apply for if you
Oh, I
it's
have
also
that.
the status.
Yeah, I am the
Yeah.
dyslexic one.
Yeah, you're the. But then I think you're allowed to sit in a different room.
I'm fine sitting with
Yeah.
everybody. That's
Yeah, okay, well, comments.
okay.
It's a small group, so
Yeah.
that's
I guess half an hour. Yeah. 20 minutes, I think. It's also.
in all honesty, I don't think they need to try to.
You got a couple? Yeah.
That was the exercise.